So in this video we'll be discussing about vibrational spectroscopy. So vibrational spectroscopy deals with the study of molecular vibrations and how molecules absorb infrared radiation to move between different vibrational energy levels. So in order to understand this, we first use the harmonic oscillator model where the chemical bond is treated like a perfect string. So this model works only for low vibration energy because near the equilibrium bond length, the potential energy curve is stable, or we'll say nearly parabolic, and also the restoring force is proportional to the displacement. However, this model is physically unrealistic for real molecules because it predicts equally spaced energy levels and does not allow the bond dissociation. So the selection rule in case of the harmonic oscillator is delta nu is equal to plus or minus 1, and the energy level here in case of harmonic oscillators, the energy levels are equally spaced and the potential is perfectly parabolic, whereas in case of the non-harmonic oscillators, the energy levels are not equally spaced. We'll study more about it later in this video. They say that in case of the non-harmonic oscillators, as the energy level increases, the levels come closer and closer and closer. So that's the case of non-harmonic oscillators, and we expect a single fundamental absorption like in harmonic oscillators. But in case of non-harmonic oscillator, we'll be studying more about overtones, hot bands and stuff. So let's see. So yeah, experimentally HCl has multiple peaks. This tells us that the real molecular oscillators are in harmony. So so we take the assumption of anharmonic oscillators. So here what anharmonic oscillator says is that it's a correct opposite of whatever we said about the harmonic. So they said that okay, I think I was explaining that harmonic oscillator, the restoring force is proportional to the displacement, but whereas in case of anharmonic, they isn't proportional to this one, and it also fails due to the large bond stretching. That means dissociation will happen. But whereas in case of the harmonic oscillator, if you remember in the beginning of the lecture, I was saying that harmonic oscillator predicts that equally energy levels are there, and it does not allow bond dissociation, and then the potential energy curve is nearly parabolic and the restoring forces is proportional to displacement. There are 4 points which are harmonic oscillator was saying, and the correct opposite 4 points is what anharmonic oscillators are explaining. Okay. And also in case of lower vibrational energy, only the harmonic oscillators work, the model work, whereas in case of higher vibrational energy, anharmonic oscillators work because of the stretching, because of bond stretching and dissociation, anharmonic this thing is activated. So in order to overcome these limitations, as you say, it's just a theoretical thing. So harmonic oscillator is just a theoretical thing, and for real molecules we say about the anharmonic oscillators. So this is the graph. This is equilibrium R. If the R is greater than R equilibrium, so the distance between two nucleus is greater, that means they try to attract, right? But then when this thing is very close, so that means R is smaller than R equilibrium, they try to repel it. So we can say for R greater than R equilibrium, it is due to nuclear repulsion, and if R is greater than R equilibrium, is attraction. So there's something called the Morse potential. So as I said, restoring force is not proportional to displacement, energy levels is not periodic. So in order to overcome these limitations, we use something called the Morse potential. So Morse potential is a more realistic potential energy function that accounts for, like as I said, bond stretching, anharmonicity, dissociation. So at low temperature, as I said, it behaves like a harmonic oscillator, but at higher energies, the energy level becomes closer together. So whatever I'm saying is just a repetition of points, so that you just, all these points remains in your brain. So you feel repetitive, but it's fine. The energy levels become closer together and eventually lead to bond breaking. So yeah, so this is the Morse potential equation. dE 1 minus e raised to minus a r minus ra the whole square. So where d is a dissociation constant, and we'll be using this to understand the curve. So yeah, a is a constant, r is equilibrium bond length. Okay, yeah, so let's take a case where r is infinity. So if this is infinity, e raised to minus infinity is 0. So this whole term becomes 0. So it's just dE 1 minus 0. So V of R is equal to dE. That correctly predicts that the dissociation, finite dissociation energy. So if you say that two particle is very farly kept, very distantly kept, they have strong nuclear energy, and the potential energy is also very slow, and the bond is also stretching because of the length. Okay, and in case where R is less than Ra, then obviously its repulsive force, potential energy increases steeply, and yeah, that's it. So yeah, and next, in case where R is equal to Re, the Morse potential is equal to the harmonic potential. Molecule is most stable, potential energy is minimum, and the forces of attraction and repulsion balances. So these are the three cases of Morse potential. Next, let's explain the experimental IR spectra. So using the Morse potential, the vibrational energy levels are not equally spaced. So this is the nth time I'm saying that the vibrational energy is not equally spaced. Energy spacing decreases with increasing in the energy of frequency. And about the overtones. So you will come across certain terms called the overtones and hot bands. So we'll see these terms again later. Before that, let me explain about the Morse potential. Let me explain more about Morse potential. So if we use Morse potential in harmonic oscillator problem, instead of half kx square and solve Schrodinger equation, we obtain the quantized vibration energy level as this one. So this is the E nu, where E nu is equal to V plus half H nu E minus V plus half the whole square. H nu E is chi E. So this term alone, if you take this term alone, it's a harmonic oscillator. So V plus half nu E H is equal to the harmonic oscillator. But whereas if you have this extra term V plus half the whole square H chi E nu E, this whole full term is for the anharmonic oscillators. So where V is the vibrational quantum number, and nu E over here is the fundamental vibrational frequency, and chi E is a harmonic constant. Fine. So there's this table over here. So in case of harmonic oscillator, bond dissociation does not happen. Morse potential, there is bond dissociation. Harmonic oscillator energy spaces are equal, whereas in case of Morse potential, it keeps on decreasing. So it will be, initially it will have a gap, but as you go up, the gap decreases. So due to anharmonicity, the energy spacing is decreasing, and overtones is not seen in harmonic oscillators, but we can see it in case of Morse potential. So for harmonic case, I just showed you before, the first term alone is for the case of harmonic. Nu is the frequency of the photon observed. Okay, yeah. So now let's take an example of transition. Nu is equal to 0 to nu is equal to 1. But before that, I would like to find the value for nu E, this one. I would like to find the value for this one. So to do that, let's take the case of the harmonic case as well as the anharmonic case, substitute this value over here to this side, so you will get like this, and then writing in terms of nu, you will get this gets cancelled. Nu is equal to 1 minus 1 plus v chi e, and then what you do is that we will use the Morse potential next. So Morse potential was d e 1 minus e raised to minus a r minus r equilibrium the whole square, and I'll take this term as to be x to simplify my math, and then what I do is using the Taylor series, I'll get like this, and then I get like this. You just square it. So next I'll do is I'll multiply and divide it by 2. So this will be in the form of 2deax square. So this one is k, and using k, I write the equation for nu e is equal to 1 by 2 pi root of k by nu. K is nothing but this one. You just have to substitute, and you'll get the value of nu e. And to this equation, you just substitute the nu e. So this is how the new equation looks like. So because in the anharmonic term is subtracted, the net increase in energy becomes smaller and smaller. This means that the energy levels get closer and spacing between the successive level decreases. So here you can see I have differentiated the energy levels according to harmonic and anharmonic. Here you can see the value is from nu e 3 by 2, 5 by 2, 7 by 2, whereas here there's extra terms. So use the equation 1 plus 1 by 2, 1 plus 2 plus 1 by 2, and 3 plus 1 by 2. So yeah, like that. And here the same thing, but there's a square. So it was 1 plus 1 by 2 the whole square, then 1 plus 2, so 2 plus 1 by 2 the whole square, like that. That's that. So that's harmonic oscillator term and anharmonic. So this is how the energy levels look like. So if we compare the harmonic and anharmonic solutions from Morse potential, the constant is positive number, hence subtracting from standard value, the energy level, say that as quantum number increases, the energy level is decreasing. That is, as you go higher level, the line gets more closer. So let's take the example of this one, 0 to 1 transition. So here I can say 0 to 1 transition. So this is the ground state to first state. So if you subtract the energy level delta E, what I'll get is, sorry, this is a delta E, this is delta nu. If you see H cross, then sorry, not H cross, H, that is energy, but here there is no H, so you can say it is delta nu. So subtract these two, you will get nu e, I guess, nu e, and nu e minus 2 nu e chi e, I guess, yeah. Yes, so as frequency decreases due to anharmonicity, and also this explains the red shift of the vibration bands. Next one is the effect of harmonicity on selection rules. So as the energy values get closer and closer, the selection rule is delta nu is equal to plus or minus 1. But for anharmonic, the additional transition happens. So there's this thing, it can go from 0 to 2 or 0 to 3. So stuff like that can happen. So if it is 0 to 1, it is fundamental. 0 to 2 is first overtone, and 0 to 3 is the second overtone. So I'll say this one fundamental, first overtone, and the second overtone. And certain things can, instead of going from the ground state, can jump from the first excited state to other states. So these are called hot bands, right? Okay. Yeah. So first we'll discuss about the overtones, and then we'll jump into the the hot bands. So yeah. So let's take the case of first overtone, nu v plus 2, and what you do is we have this equation nu E plus so V plus half nu E, that is delta nu, okay, is equal to minus V plus half square nu E chi E. So here the state is V plus 2. So instead of writing V alone, we write V plus 2V. So it will be V plus 2 plus half like this. And then this. So you open the brackets. So you will get V plus, this is 5 by 2. And then again 5 by 2 the whole square. Okay. Now what I'll be doing is that if I take this thing common, I can subtract these brackets, right? So it will be V plus half, V plus 5 by 2 minus V minus half. So this V gets cancelled, so you'll get 2, right? This will be 5 minus 1 by 2, that is equal to 4 by 2, which is equal to 2. Similarly, I'll do the case of this one. So I'll take nu E chi E common. I'll get V plus 5 by 2 the whole square plus V plus 1 by 2 the whole square, and then solve the thing. And I can use this identity, a square minus b square ka identity, and solve this. I'll get like this. So finally the answer for first overtone is 2 nu E minus 2 into 2 nu plus 3 nu E chi E. Okay. Apart from these overtones, as I said, with weak frequencies, there are other weak bands that appear in the IR spectra, which is called the hot bands. These are not overtones but transition originating from the thermally populated excited vibrational state. So, and the population is the intensity is of the hot band is proportional to the population of the initial state. So hot bands are much weaker than the fundamental this thing, and the hot bands appear only in the IR spectra due to anharmonicity. This anharmonicity makes energy bands closer at higher levels. So it's, as we said, fundamental frequency is higher than the hot bands, and after that, so it will be first is fundamental frequency, first overtone, second overtone, and maybe hot bands, and second overtone can be a bit similar. So the frequency of the hot bands is always less than that of the fundamental frequency. So as temperature increases, excited vibration state increases, intensity of the hot band increases, intensity of the fundamental band decreases. So we can say that we can differentiate overtones and hot bands by saying overtones are temperature independent, whereas in case of hot bands they are temperature dependent. And overtones always start from the ground state, whereas hot bands always start from the excited state. So V0 to 1 is called the fundamental, V0 to 2 is first overtone, and V0 to 3 is the second overtone. And these are the anything jumping from excited state. The first state to any other state is called the hot bands. So that's it for today's video. See you in the next one.